Hi everybody, welcome back to the Feynman technique. So today we're going to be solving the Gaussian cosine integral. And our goal is to solve for I of b, and the parameters a are constant and b is our variable. That allows us to treat this as a function of b. Now let's get our initial condition for this function. So if we plug in 0 for our b, this entire part goes to 1, right? Because cosine of 0 is 1. So we just have this. And in our last video, or one of the previous videos, go back one or two, we derived a formula for this. And it's square root of pi over 2a. So we have I of 0 equals square root of pi over 2a. So now we're going to take I prime of b, and we're going to use differentiation under the integral sign. All right, so that allows us to pass the derivative inside the integral as a partial. And since this part does not depend on b, we treat it as a constant. So we're only taking the partial with respect to b of that. Okay. Now the partial with respect to b of cosine of bx, again, with respect to b, meaning x is constant. We take that derivative and we get negative x sine bx. So now this is I prime of b. All right, so we can solve this using integration by parts. Let's see. We're going to pick u is equal to this part right here. And we're going to pick our dv equal to the rest. So it's just negative this whole part right here. This is going to be our dv, and of course with the dx part also. So we have u and dv. That implies that du becomes this and v becomes this. This is a fairly simple antiderivative to take, and this is its antiderivative. Okay, so we plug that back into our integration by parts formula, and we have this. We have this term evaluated at some bounds here, 0 and infinity, minus a new integral. All right. Those bounds evaluate to 0, by the way. At infinity, this part is going to cause the thing to go to 0, and at 0, this is going to cause the thing to go to 0. Remember, we're letting x go to 0. And x go to infinity, not b. Okay. So now we have I prime of b equal to this junk right here. And this is a constant, which in the next step, we will factor right out of the integral. And also, we will note that the remaining integral is simply our I of b. So this results in a separable differential equation. All right. So we have I prime of b equaling this constant times I of b. All right, so we have this differential equation now. This is separable, so let's separate it. We put all our I variables on one side and all our b's and db's on the other side. And we have this, and these are simple integrals to compute. So we have integral this equals integral this. So natural log I is equal to this. We exponentiate both sides to get this, and then we'll treat e to the c as its own constant a. And now we'll use the fact that I of 0 equals square root of pi over 2a to determine that a has to be, or our I of 0, has to be square root of pi over 2a. And now we have the final answer to our original problem. So, oh, I don't have it displayed anywhere on the board here. So, well, let's reset it. And this integral right here is equal to that. Sorry, I don't have the actual answer pasted fully here or displayed fully here. But hopefully you remember the integral that we started with. Anyway, guys, hope you enjoyed that, and we'll see you next time.